Determine the E field at P if the charge magnitude on each particle is 800 nanocoulombs. So you can see here in the diagram, this is point P. It is located 3 meters away from the origin. Here are the two particles, and they are each located 4 meters away from the origin. And the goal here is to determine the net electric field at point P. And to do that, we have to determine the individual E fields created by these two particles. So starting with the positive charge, remember that the E field created by a positive charge radiates outward, radiates away from the positive charge. So that means it would be radiating like this in the direction of P. And so if I want to draw the E field at P, it's got to be parallel to that line I just drew. Yeah, that's good. There we go. Parallel to the line I just drew. There we go. Okay. Now for the negative charge, the E field still radiates, but instead of radiating outward, it radiates inward. Okay. And so consequently, it looks, here's the line that matters. Oops. And the line I want to draw is parallel like so. Okay. Now I need to label these two E fields so I don't get confused. So let's call this particle A, we'll call this particle B, so that this is the electric field due to A, this is the electric field due to B. And the net electric field has got to be EA plus EB. So this is just vector addition. So immediately I can say, oh, okay, so the net X has got to equal EAX plus EBX. And I can write the same thing down for Y. I'll be doing that in a little bit. Okay, great. So this is a vector addition problem. We know how to do those. Before I start into getting these X and, components, and I'll need the Y components too, let's figure out the magnitudes, because I know I'm going to need those. So EA is going to just be K QA over R sub A squared. Okay, K, we know that's 9 e to the 9th, E9. And Q, that's 800 E negative 9. And we got to divide it. Now I need the distance from A to P. Now since this side is 3 and this side is 4, if I draw that side right there, you could do the Pythagorean theorem. I happen to know this is going to be 5 meters. Okay, great. So since that's going to be 5 meters, this is going to just be 5 squared. Okay, so go through the calculation now. And I get 288. So that's the electric field at A. That's newtons per coulomb, of course. That is not my final answer for this problem, not even close, but I have figured out the magnitude for A. Now, let's do the magnitude for B. Just for saving space, looking ahead, I'm going to do that up here. Okay, it's going to be K times QB over RB squared. And if you look closely, we already know that's 9 times 10 to the 9th. QB, well, we already know that. The charge magnitude on each is 800 times 10 to the minus 9th. Okay, and RB, well, that's going to be this distance right here, but again, I'm going to have that 3 and that 4. This is just going to be 5. So it's going to be the exact same thing, which means EB is just going to be 288 newtons per coulomb. So they're both creating the same magnitude of E field. The directions are different, and that's key. The directions are different. Okay, so to get the net, I need to say, all right, E net x, this is going to be EA. Now I'm going to need an angle. Okay. So let's say I'm just going to take the horizontal here. There we go. I'm going to take the horizontal, and I'm going to call this angle right here. Well, we'll just stick with that. We'll call that theta. And you'll notice that angle theta has to be the same as this angle theta. And I know that because this line is horizontal, this line is horizontal. And this side here that I drew is parallel to EA. Okay. So when I want the x component, that's going to be the adjacent side. So that's going to be cosine of theta. Now, I'm going to do a similar thing for EB here. Now notice, by the way, EB is also pointing to the right. It has a positive x component. So this angle is actually also going to end up being theta. How do I know that? Because if I draw this here, this angle here has got to be the same as this one. Okay, that's great. And I know that this angle and this angle have to be the same because these are similar triangles. They have all the same sides, which means they have to have all the same angles. So these angles have to be the same. And since this is horizontal and this is horizontal and they're both relative to the same line, they both have to be theta. So consequently, that is also going to be cosine of theta. And in both cases, I know with the electric fields R, that's 288. And the cosine in both cases is going to be adjacent over hypotenuse. The adjacent is 4, the hypotenuse is 5. So that's going to be 4/5. Okay. And that works out to be 460.8 newtons per coulomb. Okay, so now I know the x component of my net E field. All right, so now let's do the y. So that's going to be E net y. That's going to equal EAY plus EBY. Okay, so E net y. Okay, this is going to be EA sine of theta. This is going to be minus, because EB is pointing down. So this is minus EB sine of theta. And you might already see the punchline. I'm going to work through it all the same. The sine is the adjacent over the hypotenuse. The adjacent is 3. The hypotenuse is 5. Minus 288. And hopefully you can see here, I'm subtracting, both terms are the same. And so this means that the net in for the y component is 0. The y component of the net electric field is 0. And so I've got my answer. That means in this case, since one of my components is 0, that means the net electric field is an axis vector, and it's pointing horizontally. There we go. That happens to be E net right there, and this is the magnitude. So I now know the direction and the magnitude of the net electric field.